Hello, I am Ethan Pickering, a new postdoc here at MIT, and I'll be introducing my research on the discovery of extreme events via optimal active sampling and neural nets. So what is an extreme event? Well, an extreme event is one that occurs near or past the upper or lower range of historical measurements. And there are numerous examples of extreme events, such as weather phenomenon. We can think of flooding, earthquakes, tornadoes, heat waves, or rogue waves. But there are many other extremes than weather. There are extremes in health systems, such as predicting precursors to pandemic spikes, or infrastructure, particularly cascading electric grid failure. And each of these extremes are becoming much more common. And all of these fall under risk quantification, but there are also other extremes that can be found in design problems, such as genome editing or path planning. So what are some characteristics and the challenges? The first characteristic is that extremes are, well, extreme. They have high magnitude in certain observables. Two, they are rare, and so limited data is a significant challenge for characterizing them. Three, they appear from seemingly benign or unassuming conditions, posing a significant challenge in finding the regions associated with dynamical instabilities. Four, they're nonlinear and transient. And five, they belong to infinite dimensional systems, meaning the parameter space is too large to effectively simulate. So our goal here is to use data from simulations or experiments to characterize extreme events, but due to those challenges, we need to be smart about how we select data. To illustrate this, we start with some cartoon function here that is a function of a random variable x and observable output y. We call the regions with high magnitude as extreme and regions with low magnitude as average. Now, how would you look to acquire data to describe this function? And in general, this is done by reducing uncertainty in space via exploration. And say we are given a number of initial data. To reduce this uncertainty, we'd likely choose a point far away, and then something that splits the gap, and etc. But you might notice that there is a problem here if x goes to infinity, meaning sampling this way is not generally tractable. So to reduce this space, we impose some domain knowledge via exploitation and add weights to our acquisition function. And so a proposition that we have recently introduced is a ratio between the probability distribution of the input and the output. And if we apply this to the function above, we can see that it finds a balance between something that is likely and something that is extreme. So our framework for learning and discovering extremes is as follows. We begin with some limited input and output data, and we pass this to a surrogate model, such as a deep neural net, which is uniquely suited for this task. And we train the model and use it to predict extremes, and then pass this information to our optimal selection algorithms mentioned in the previous slide, and then inform the next experiment with what will be the most informative information to discovering extremes. So then once we pass this data to our simulation or experiment, we loop until converged to create our finally extreme model. So hope to see you all at MIR.